talk, and then we have a 2-hour break for lunch that's on your own, and then be back here at 2. So yeah, take it away, Ryan.
The introduction. This is joint work with my wonderful co-authors Henry, Emma, and David, and it's based on work that's going to appear at Usenix Security this year. So in order to build better products, developers want to understand how their applications are being used. So for example, WhatsApp might want to know what fraction of users blocked a contact today. The way they would answer this type of question today is they would just gather a bit from each user, indicating whether that user blocked a contact or not. Now, the problem with this is that WhatsApp started with a population-level question, right? But they're getting more information than that. They're learning something about every single user in the system. And while this question might seem a little benign, WhatsApp might ask a more specific question, like what fraction of teen users blocked a contact today? So now they're learning something about both the behavior and demographic characteristics of each user in the system. You can imagine in practice, WhatsApp might ask many questions, such as, did you enable disappearing messages? Did usage increase while you were traveling? And all of this kind of composes to build detailed user profiles with sensitive information. And in many applications, so for the case of WhatsApp, there's other kind of leakage that can combine with this. So WhatsApp also knows who you talk to. So now they're learning something not just about kind of who you are, but also your relationships. And so the kind of goal would be that WhatsApp can still ask these types of questions, but they just learn kind of the population level answer, not this individual data. And a tool, a potential tool that we could use to do this is something called private aggregation. So private aggregation takes kind of raw user data as input and outputs just an aggregate or a sum over that data. So it's a simple type of measurement, but you can support things like histograms or even model updates in the context of federated learning, or this question that I posed a second ago. Okay? And private aggregation has kind of, or the schemes we'll see today, have 2 strong properties that we're interested in. So one is privacy. So even if WhatsApp is malicious, they can't learn kind of anything more than the aggregate sum. And even though they don't see kind of individual user data, they can still reject invalid reports. And so in this context, what I mean by invalid report is that maybe the client was supposed to only give a bit, but they give a really large integer to bias the measurement, or maybe they just completely give a malformed message in order to abort the computation. So in either of these cases, WhatsApp will be able to kind of detect this and remove the client from the aggregation. Okay, so this is a powerful tool, and I think the dream would be that kind of most applications that we use today at least replace some of their telemetry with private aggregation. And it seems like we've been on track to do that. So we've had kind of decades of research. We've had a standardization process that's gone on for many years now. We have open source, kind of well-maintained private aggregation systems, and we've seen real-world deployments by big tech companies like Apple, Google, and Mozilla. And yet, kind of when we look to real-world use, it's only a handful of applications today are actually using private aggregation. And from talking with like a few people who have worked on this problem for a while, the question comes up, are we actually making progress here? Like we've had tons of effort from people in this community for building this tool, and it's not taking off in the way that we would hope. Now, I think the answer to this question is yes. I'm very optimistic about this technology, and I think in a broader context, it makes sense why it hasn't taken off the way that we would like. And so that's what I'll talk about today. How do we drive adoption of private aggregation? And I'm going to do this in a few steps. So I'll first look at a technical barrier around deployment. And then I'll propose kind of a new aggregation model that gets around this barrier and a scheme within that model. And then we'll evaluate it at the scale of 10 million simulated users. And then at the end, I'll talk about some kind of additional barriers that I think need to be overcome for this technology to take off. So a running example that I'm going to use throughout the talk is the example of TLS, a big success story of cryptography. And in particular, if we look from the years kind of 2014 to 2019, we saw a huge rise in adoption of TLS from something like 30% of page loads to 80% of page loads. So why did this happen? Well, in 2014, certificates cost money. And this hindered adoption not just because of the dollar cost, but you can imagine if you're a developer who wants to use this technology, you have to pay an external company. And that probably requires talking to your manager. You might need a business contract, which might involve lawyers. The whole process just gets more complex. So a group of people noticed this, and in 2015 started a nonprofit called Let's Encrypt that offered kind of free certificates on the web. And this is widely seen as kind of one event that really led to this adoption rise. The second event, which we'll talk about more later in the talk, is that browsers began to incentivize TLS. But the main takeaway here was that what TLS did was they made kind of the tool free to adopt, and they incentivized adoption of the tool. So when we look to private aggregation, and today I'm going to focus on the schemes that have been the subject of standardization for the last few years, One problem with them is that they require two servers. So it's not just WhatsApp that's talking to all their clients. There's also a second server that's talking to all of the clients. And the work and communication of each of these servers is scaling kind of with the number of clients in the system. So if you can imagine kind of millions of users, this is a heavy workload. Now for privacy to hold, we need these servers to be run by separate entities. So WhatsApp can't run the second server themselves. So this raises the question, who runs the second server? And the answer today is you pay some third-party service, such as DivvyUp, to run this service for you. But as I told you about a slide ago, kind of paid services were exactly the thing that hindered TLS adoption. And so our hypothesis is that the same exact thing is happening here in the context of aggregation. So our solution to this problem is to follow exactly in Let's Encrypt's footsteps. Let's have a nonprofit kind of run this second server for free for anybody who wants to use it. And again, this is just following exactly what Let's Encrypt did for TLS. The problem is that we're not issuing certificates here. We're doing aggregation. And this is a much heavier workload. So in particular, the second server in this world is working as hard as the application server. And so if you imagine even just thousands of applications, each with millions of clients, this is not a scalable workflow for a nonprofit to run. So the goal of this talk is to drive down the cost of the second server. And in particular, the technical goal I'm going to have is I want to build a second server whose cost is independent of the number of the clients in the system. Okay, before we dive into this, I'll mention there is an alternative solution, which is that you just get rid of the second server entirely. So there's been a rich line of work that essentially samples a subset of clients to run an MPC to emulate the work of the second server. And so now instead of needing kind of a separate entity to run this thing, you need to assume that some fraction of clients in your system are honest. Okay? There's been many kind of works in this space. I think we'll hear about a few of them later today. I won't be able to summarize all the kind of complex set of trade-offs here. The cleanest distinction I'll give you between this world and the two-server model that we'll work in is at the moment we don't have an existing kind of single-server private aggregation scheme that gets both privacy against the malicious server and robustness against malicious clients at the scale of, say, 1 million users or a small number of users and many inputs. Okay? That's all I'll really say about this kind of world right here. The schemes that we'll look at will get both of these properties at 1 million user scale. So we'll focus on the two-server model for now. Later in the talk, some of the other barriers that I'll mention will also apply if you were to go down this route as well. OK, so now I'm going to propose kind of a new deployment model that pushes us towards that goal of a cheap second server. So on the left, we have private aggregation today. Okay? And so kind of each client is talking to both servers. And our proposal is what we're going to call heavy light aggregation. So in particular, there's going to be a heavy server that still talks to all of the clients. So we envision the application provider running this. And then there's a light server who doesn't talk to the clients. Okay? And we envision the nonprofit running this. And the key kind of asymptotic goal that we have is that the communication and work of this light server should be sublinear in the number of clients. Okay? Yeah?
It seems like the light server can decrypt and can obtain the sum, right?
Mm-hmm.
And that is potentially problematic because I suppose WhatsApp may not want the light server to know that sum. It's a proprietary sum of some sorts that they want to use to enhance their products. They may not want to share that sum openly or publicly. Is that a problem you envision, or?
Yeah. So the question is essentially, if a light server can decrypt and get the sum, is this a problem if, say, WhatsApp is the one who wants the measurement? So I think you could have a pretty easy extension to our scheme where the light, let's say, the heavy server here can kind of secret share the ciphertext that it gets, and then the light server proves that it decrypts its part correctly. So I think you could add essentially zero-knowledge proofs on top of our protocol. That shouldn't be too expensive. That would get you into the world that you're talking about, if that makes sense. OK, cool. So we're going to try to build an aggregation scheme in this world. One problem with it is that protecting against the malicious heavy server is very hard. And I'll give some specific attacks in a second. But for now, I'll just mention that the way that we're going to get around this is we'll allow some one-time setup. So we'll allow the light server to talk to each client kind of once. And then never again. And we'll assume that clients participate in kind of many different statistics over time to amortize this cost. And I'll mention here that the setup can be reused across different applications. So it's done per every logical client, not per application per client. OK, so let me illustrate why this is kind of a difficult, or what the heavy server can do in this setting. I'm going to give you a straw man scheme based on additively homomorphic encryption. So just kind of recall, additively homomorphic encryption, we're going to look at a public key kind of setting. So if I encrypt some message with a public key and decrypt it with a secret key, I get back my message. But I have this key kind of additive homomorphism property that says that if I have two ciphertexts of different messages, I can combine them in such a way that I get a ciphertext that encrypts the sum of those two messages. So with this tool, I can build kind of a strawman scheme in the heavy light aggregation model. So how does this work? Well, the light server holds kind of the secret key for this encryption scheme, and the clients hold the public key. And each client is just going to encrypt their input underneath this encryption scheme and send it to the heavy server. And the heavy server can sum up kind of all of these ciphertexts and give the single kind of result ciphertext to the light server here, who decrypts and gets the aggregate. So there's kind of two attacks I'll point to if we use this tool. The first attack is that a malicious heavy server can drop kind of submissions from honest clients. So the heavy server could just generate the aggregate ciphertext as just being the first user's kind of ciphertext. And now this is a problem because we're leaking the exact input of a specific user. Another type of attack comes up if we imagine, again, doing many statistics over time. So here's kind of the same picture, but now I'm going to run 2 rounds of aggregation. And something the heavy server can do is they can use, let's say, the first client's input again in the second round of aggregation. And so again, we're learning something more about kind of a single client's input than we should. Okay, so these are just 2 attacks to kind of illustrate that it's a little bit difficult to kind of build a secure scheme in this model. So I'll show you kind of how we do this. So we introduce a new aggregation scheme called HELI, or Heavy Light Private Aggregation. It's based on work to appear at USENIX this year. It consists of 3 components. So one is a tool called aggregation-only encryption, which is essentially very similar to the additive homomorphic encryption I just showed you a second ago, but it's going to stop the attacks that I described. And then there's 2 additional components we have. So in order to get robustness against malicious clients, we're going to use zero-knowledge proofs. So this just uses kind of standard proofs in the literature. We don't do anything new here. And then we also give some mechanism for clients to validate their identity during setup. So for example, using Apple's AppAttest. So today we're just going to talk about this first piece, this aggregation-only encryption. 2 things I'll say about it really quickly. It's a very simple twist on existing aggregation schemes. So if you kind of miss something about the details, I did a poor job of presenting it. And secondly, we instantiate it with elliptic curve cryptography, but we think it's plausible that you could swap out the underlying primitives with post-quantum secure ones and get a scheme that's post-quantum secure. But we don't prove this. Cool. So in terms of cost, after kind of this one-time setup, we achieve our goal. So we get a light server whose work and communication is constant. Okay? With the caveat that if some clients drop out after setup, the heavy server has to tell the light server which clients dropped out. And so we incur some costs based on that. But if you're kind of in this happy path here, this O of 1 is actually 1. So the concrete cost kind of for every integer I want to aggregate is 1 exponentiation of work and communicating 1 group element. Cool. So this is kind of the high-level asymptotics. Now I'll tell you about aggregation-only encryption. And so, yeah.
What about the communication in terms of the size of the input?
Yeah, so it will scale with the size of the input. Yeah.
For both the servers?
Yes, so the light server, so if you had L kind of inputs, this would be L here, and the communication would be L. Yeah, good question. Yeah.
Sorry, higher level question. So you were saying that you think the reason that private aggregation is not being adopted is because is it because of the cost of running that second server?
Yeah, so I think it's a deployment problem. I think partially it's the cost of running the second server, but I think it's more so kind of the moment you have to pay some external kind of provider to run a service for you, that involves kind of business contracts, which might involve lawyers. Like it's a whole, like it's a much more difficult process than just I want to install this library and use it in my system.
But does this solve that second problem?
Yeah, so the kind of vision that we have is that we remove completely the cost of the second server. So the nonprofit, let's say, could run this thing for free, and there's just like an API that anybody can call to use this thing. So basically, you remove the need for, let's say, this business contract between a company and another provider.
But who's paying for the nonprofit?
So the nonprofit would pay for this. So the whole point is, like, let's make this server so cheap that a nonprofit could feasibly run this at scale for the internet.
Forgot to say, we're supposed to use the microphone for the recording, so I'll try to remember to pass it if you have it.
Yes. So I think we'll like partially get to that goal, but we'll see later in the talk. So, okay, so I'll talk about aggregation-only encryption. I've highlighted the differences between additively homomorphic encryption and this tool. And the main difference is now, instead of a public key, we're going to have specific keys for each client. And then each ciphertext is going to be bound to a specific round identifier. Okay, so if I have kind of multiple statistics that I'm measuring, each client submission will be kind of bound to that statistic. Okay, and then decryption can fail in some settings, which I'll explain in a second. So the additive homomorphism property remains exactly the same. So I can take two ciphertexts and I can combine them to get an encryption of the sum of the messages. But correctness is slightly different. So what correctness says is that I can decrypt a ciphertext successfully if that ciphertext is the sum of kind of all clients' messages for a specific round identifier. Okay, so the way to think about this is the attacks that I showed you before. If a heavy server tries to, say, drop out a client submission or replay a client submission across rounds, decryption will fail here. And then the next kind of property that we'll want is compactness. So we want kind of the runtime of decryption to be sublinear in the number of kind of client-specific keys that we have in the system. Cool. So now I'll show you how to build this thing. So our starting point is going to be from a basic kind of two-server private aggregation scheme, and I'm going to massage this thing until we get an aggregation-only encryption scheme. So the way that this scheme works, clients encode their inputs over some group, and they secret share them to both the application server and the second server. And both of these servers kind of sum their local shares and then reveal the result. And as I mentioned, we're going to be interested in amortizing costs across many different statistics. So what I'm going to do now is zoom in on kind of the client and the second server as we run multiple statistics over time. So in each round, the client is going to secret share their input, and the second server is going to compute a sum over all the randomness that it receives. And the main takeaway here is that the second server's cost, both in terms of communication and work, scales both with the number of statistics you measure and the number of clients in the system. And so we're going to drive down these costs in two steps. First, we're going to use PRF to drive down the cost of communication, and then we'll upgrade our PRF to something called a key homomorphic PRF to drive down the work. So step one, super kind of simple crypto trick. When we secret share, instead of using kind of truly random values, we're going to use pseudo-random values. So the client will use a PRF to do this secret sharing. And now, instead of sending all of these random values to the second server, they can just send a single key. Okay? And then the second server can compute the PRF outputs themselves, and the protocol is the same. So we've reduced the communication, but the second server is still doing a lot of work. So to reduce the amount of work, we're going to need a new tool called a key homomorphic PRF. So this has the same notion of security as a standard PRF, but it has this nice key homomorphism property, which says that if I evaluate the PRF twice on two different keys but the same input, I can combine those evaluations to something that's equivalent to a single PRF evaluation on the sum of the keys. And this is not some crazy crypto object. I can give you a key homomorphic PRF in 2 lines. Say we have some hash function to a DDH hard group. I can just hash my input and raise it to the power of the key, and that's a key homomorphic PRF. And before I show you kind of how we use this, I'll mention there's prior work, Lerna and OPA, that work in this single server aggregation setting that use key homomorphic PRFs in a very similar way to what I'm about to show you. So this is the same picture from before. I haven't changed anything except now I'm using a key homomorphic PRF. The only difference or observation that I'm going to make is that in each round, the second server is computing a sum of PRF evaluations. But with a key homomorphic PRF, this is actually equivalent to a single PRF evaluation on the sum of the keys here. And the sum of keys is shared across kind of all the statistics. So the simple idea is let's just compute this thing once at the beginning, and now in every kind of round of aggregation, I'm only computing a single PRF evaluation. So by doing this, I've now have the work is also independent of the number of rounds that I'm doing. So this is basically it. To show you how you get an aggregation-only encryption scheme from this. So first, the kind of tweak I'll do is the light server is going to generate all the keys for clients, and it will send them to clients. And then it will compute the sum of these keys. That's the gen algorithm right there. For encryption, the clients, again, just evaluate this key homomorphic PRF and use that result to mask their input. And then for decryption, essentially all the light server does is compute this kind of one PRF evaluation and use that to unmask the result that it receives from the heavy server. Okay, cool. So I'm not going to go into details about dropouts. It's pretty simple. You can imagine when the light server kind of generates each client's key, it uses a PRF to generate the client's key. And then the heavy server then can tell the light server, okay, these clients dropped out, and the light server can use that PRF to compute kind of the missing pieces of this mask here. Okay, so that's essentially our scheme. Now let's evaluate this thing. So we implemented Heli in Rust over the Ristretto 255 group, and the baselines that we're going to use are Prio and Whisper, which are two kind of prior work that have been the subject of standardization. And the setting is that each client is going to submit a vector of 1-bit entries for aggregation. So for example, this question that I posed at the beginning of the talk would be one question that you could answer. So we evaluated an aggregation workflow end-to-end on AWS over 10 million simulated clients where 10% drop out, and each client is submitting 32 1-bit inputs. So I'm going to show you kind of the cost of each one of these servers in the system. So using Prio, we get some cost. The main thing I want you to notice is that the cost of both the heavy and the light server is the same. And even if we use a kind of follow-up work that improves on this cost, again, the works of both servers are the same. However, if we use Heli, we get this asymmetric cost model. So in particular, the heavy server is doing costs 38 times more here, but the light server costs 120,000 times less than prior work. Okay, so let's dive into these costs a little bit. Takeaway one is that Heli makes the light server's work incredibly cheap. So here I'm showing you a graph where we're aggregating a single bit over many clients. And at most, Heli's light server is doing up to 23 million times less work than a Prio or Whisper server. And if some number of clients drop out, then this number goes down to, say, 170,000. On the flip side, Heli increases the heavy server's work. Okay, so here I'm fixing the number of clients to be 10 million, and I'm summing kind of 1 to 64 1-bit inputs. And here the heavy server does up to kind of 60x more work than a Prio or Whisper server. And we didn't talk about this in detail, but the main bottleneck here is just verifying client proofs in order to get robustness. So kind of any improvements to these underlying proof systems would immediately give us improvements here. Okay, so those are all the numbers I'll give you. I guess the question is, did we accomplish our goal? Our goal was let's make the second server cost independent of the number of clients. I think yes, but with some caveats. So we require this one-time setup. Efficiency kind of requires a somewhat stable client base. And the app providers are going to pay a higher internal cost. But the main takeaway is I think Heli makes a free second server kind of much more feasible in practice. Okay, so even if we completely kind of solved this technical barrier, I think it's important to note that private aggregation won't be adopted without incentives. So in particular, compared to standard telemetry, private aggregation has higher cost. It's going to have less flexible analytics and less monetizable data for things like ads or training. So from a purely kind of economic perspective, there's not kind of many reasons why a company would want to adopt this. Yeah.
I had a question about the sort of the actual light server's cost. So to handle dropouts, the heavy server has to describe the exact set of clients who participated.
Yeah.
And so then that, maybe it's just the cryptographic part is like more or less independent of the number of clients or something. Like, it seems that you're still doing work that is somehow scaling with the number of clients, because just handling this set and doing operations based on it is going to scale with whatever the number of clients or whatever it was.
No, you're exactly right. And maybe I was not clear enough in the fact that kind of in the happy situation where all the clients are online, then you kind of get this goal that I have. But if kind of you're in a setting where many clients are dropping out and like different sets of clients are dropping out often, then this probably, you won't kind of reach that goal that I claimed. Yeah. Yeah.
So a follow-up to that is, okay, so you explained how the one-time setup cost in this scheme can be amortized across like a client contributing data multiple times, right? So one imagines, say you have a daily collection of data, like clients are reporting every day some piece of telemetry, right? Okay, but now if you have this part of the protocol where the leader gets to tell the helper, client so-and-so dropped out, that means that there has to be some stable identifier for a client that both aggregators are aware of, right?
Yes.
And hence, to some extent, like the aggregators are able to track whether an individual client, or whether a pseudonym, I guess, for an individual client participated in aggregations over time.
Yes.
Okay.
Yes. Yeah.
So, I mean, that is some information leakage, but
yes. No, you're exactly right. That is
hard to avoid.
Leakage. Yeah. I'll talk about maybe an open problem that could address this at the end of the talk. But yes, both of you are completely right. So these are kind of, I think, the downsides. I'm not going to claim that this is a perfect scheme, but I think maybe a step towards this goal that I gave you earlier. Okay, cool. So going back to kind of the weak incentives, as I just mentioned, there's very little kind of economic incentives for businesses to adopt this technology. However, this was exactly the case for TLS as well. So TLS was more expensive for companies to run, and arguably didn't really give them much benefit. And the thing that drove adoption here was platform pressure. So browsers began to issue UI warnings if a website didn't use TLS, and some search providers like Google began to degrade the search rankings of a website if you didn't use TLS. And so both of these things were kind of enough pressure to get providers to actually start using this technology. So I think for the setting of aggregation, something similar needs to happen. There needs to be some outside incentive for people to use this. So that could come from regulation. I think if we're following kind of the footstep of TLS, the most realistic possibility is that iOS or Android do something to incentivize their applications to use private aggregation. And I'll give one specific way I am envisioning this at the end of the talk. But before we get there, I'll just kind of summarize. In this talk, we looked at kind of the rise in adoption of TLS, and we pinned it to two events, kind of using like the free certificates, and then also browsers incentivizing this technology. And my claim in this talk is that if we want to incentivize, or if we want private aggregation to also be used more widely, we might be able to follow a similar path. So in this kind of talk, we focused on this free light server, or kind of the equivalent of Let's Encrypt in the aggregation world. But even if we had that piece, I think we still need some outside incentives. So for example, from iOS or Android. So I'll close with some kind of open problems on each of these fronts. So for the free light server, one interesting question, which touches on your question, Tim, is can we get a light server with constant overhead when clients drop out? Okay. So in particular, can I do this without kind of blowing up the cost of the heavy server and still having the light server be like concretely very cheap to do? Okay. I think this is an interesting question. Another one is, can you get faster client proof verification in the heavy light setting? So as I mentioned, the main overhead of the heavy server right now is verifying proofs from clients. Right now, the light server doesn't assist in that computation at all. And you can imagine there's something that they could do to kind of help speed up verification here. And then a more broad question is kind of, are there other two-server protocols that would work in the heavy light model? So the argument I've been making in this talk is one kind of deployment kind of model that we could take for deploying cryptography with two servers is making one server really cheap. So I focus on aggregation, but I think it's interesting to think if there are other cryptographic tools that could also use similar techniques. On the incentive front, I mentioned how in TLS, browsers began to give UI warnings if websites didn't use TLS. So what's the kind of equivalent UI warning for data export? I think this is actually a much kind of harder question than in the case of TLS, but I think it's worth kind of investigating. So one kind of, I think, dream scenario that I've put on the left is that platforms have much more insight into kind of what data leaves our devices and can give warnings to users about this. And you could imagine then if an application actually used private aggregation, you would get a little lock icon kind of next to these things. Okay, before I close, I want to say special thanks to Chris, who's not here, and Tim, who is here. So it was kind of Tim had many patient conversations with me about this technology, and it was those talks that both kind of inspired and refined this work a lot. But yeah, that's all I have for you today. My name's Ryan. You can find the paper and code here. Thanks for your time.
Great talk, thanks. I have a question on the client proofs. So you said anything that improves the verification time for the clients to handle malicious clients will improve your work.
Yeah.
What proofs did you use in the current setting?
We use just basic bullet proofs with a slight sigma protocol.
Okay.
So the bullet proofs are used to prove the input validation piece, and then we have an additional sigma protocol that proves that you evaluated this key homomorphic PRF correctly.
Okay, thanks.
Did you think to use class groups to avoid the discrete logarithm problem?
Yes, I think the overall cost was more expensive than what you get with the discrete log, right?
Okay, can you give you a citation?
Or you're saying, sorry.
I think that you can replace it so that, so actually you will not need to have any setup, you just have to change the modulus and then it will operate over class groups. I can give you a citation for it, but then you will not have at all the discrete logarithm issue. There's a paper called Picasso, actually, that has this homomorphic, key homomorphic PRF. I think you could
Just so I
use
understand,
it.
you're saying you can remove the setup if you use the class groups?
No,
Or-
avoid the discrete logarithm problem, right? So now you have to get discrete log to decrypt,
Yes.
right?
Yeah. I see what you're saying. Yes.
So you will not need to do it with a class group. So I think you can replace your key homomorphic PRF with the class group one.
Yeah, so the immediate problem that might be solved, I'm not sure, is that it's not, I don't know, do we have proofs that could efficiently prove, let's say, that
Yes,
you
you
compute,
can,
you do?
yeah.
Okay, cool.
Questions? Kunal, did you have?
Very nice talk, thank you. I guess two related questions. So one, I guess maybe another route I could imagine, and I would welcome your thoughts on this, was instead of the second server being so light that it can be run for free, maybe it's slightly heavier, but then we would run it inside some kind of trusted execution environment. And I guess, at least in some settings, I could imagine that some variant of this where you actually send all the, so I guess often you may want to use these things not for a single aggregation, but for a vector aggregation. And I guess currently, like the helper time is n times d. Even if you could reduce it to n plus d, that would be a huge win. And I could imagine protocols which are sort of much more robust and can avoid all of these dropout issues in that setting, where I guess the leader just sends the keys.
Yeah,
server?
I think that's an interesting design space. It's not something we looked into, but I think, yeah, that could totally work.
Interesting. Cool. Okay, so let's thank Ryan again and get on to the next talk. Ready to set up? So our next speaker is Yiping Ma, who I guess was a PhD student at Penn and is